Just to wrap up a few loose ends to do with matrices. Firstly, I'm going to introduce the cross product or the vector product of two vectors. This is something we'll need later in FP1, but for now we can certainly define what it is because it relates to matrices. So firstly, just some notation. R3, written like this, just means 3D space. It means the set of triples of real numbers. So given two vectors in R3, given maybe UVW and XYZ, these are vectors in R3, we define the vector product UVW cross XYZ to be the determinant of the matrix IJK, but IJ and K, really by that we mean the three unit vectors in R3. So this is the same as we've seen before. We define it to be this determinant, or this is also the same, it so happens, as this. Okay, so let's take either of these determinants and expand along the row or column involving IJK. So we're going to get I times the determinant of the submatrix VWYZ, lots of I, minus the determinant of UWXZ times J, and then plus the determinant of UVXY times Z. Times K. And then this is the vector product. So this is a vector. IJ and K are the unit vectors. So let's just simplify this first. So this is VZ minus WYI minus UZ minus WXJ plus UY minus VXK. So this is a vector. It's the vector VZ minus WY, UZ minus WX, UY minus V. Oh, sorry. No, this middle entry, it should be the other way around because there's a minus in front. So it should be WX minus UZ. Yeah, so that's the vector cross product. So I put one question about that in the homework, but just to see an example, let's do 2, 1, minus 1 cross 0, 3, 5. Okay, so to work out the first entry, well, so you can, if you want, do the determinant IJK, 2, 1, plus 1, minus 1, 0, 3, 5. And then, again, well, I know there's a 0 in the bottom row, but we'll use the top row again. So we're going to get determinant of 1, minus 1, 3, 5, I, minus 2, minus 1, 0, 5, J, plus 2, 1, 0, 3, K. And then we can see this is 8I, and then we've got minus 10J and 6K. So the answer is the vector 8 minus 10, 6. And you might wonder what this vector cross product represents, what the answer actually means. And this is a vector that's perpendicular to both of the two vectors that we took the cross product of. So if you have a vector u and a vector v, then u cross v is perpendicular to both u and v. And so what this means is the vectors u and v, if we were to draw them like this, they really span a kind of plane. So there's a kind of plane in 3D space spanned by these vectors. It obviously extends in all direct. Yeah, so there's this plane that's spanned by these vectors. The cross product is this red vector coming out of the plane that's perpendicular to the plane. So that's what it means geometrically. And then the last thing I want to say is, just to mention it briefly because it's important, is what are eigenvalues and eigenvectors? So I just want to introduce this. This is very important later on in all kinds of fields of maths. Given a matrix A, given a square matrix A, we say that lambda is called an eigenvalue of A if the determinant of A minus lambda I is 0, where I is obviously the identity matrix. Eigen, I think, is German for special. And yeah, so to find the eigenvalues of a given matrix, you just work out this determinant and set it equal to 0. In fact, because lambda is an unknown, determinant of A minus lambda I is really a polynomial in lambda. And the degree of the polynomial will be the dimension of the matrix. So if it has n rows or columns, then the highest power of lambda will be lambda to the n. So we'll just take a look at an example. Find the eigenvalues of the matrix 1, 1, 1, 2. Oh no, let's make it 1, 1, 1, 1. That's quite easy. So then determinant of A minus lambda I. Well, lambda I is just going to be here lambda 0, 0, lambda. So if we subtract these, we're going to get 1 minus lambda 0, 0, 1, sorry, not 0, 1, 1, 1 minus lambda. And that's equal to 0 if lambda is an eigenvalue. So then the determinant of this is 1 minus lambda squared minus 1, which we can quite easily solve to find lambda. So lambda is going to be 0 or 2. And in fact, I mean, this matrix A is singular, isn't it? So for any singular matrix, 0 is always an eigenvalue, which makes sense from the definition. If the determinant is 0, then certainly the determinant of A minus 0 times I is still 0. Yeah, so we've got these two eigenvalues. And then what is an eigenvector? An eigenvector, V, satisfies AV equals lambda V. So if we multiply the matrix A and the vector V, we get the same thing as lambda times V. So eigenvectors are not unique in general. There might be lots of vectors. In fact, there's the whole eigenspace of vectors that satisfy this. But let's just find the vectors corresponding to each of these eigenvalues. So if we take the eigenvalue 2, we've got 1, 1, 1, 1. V, that's something we don't know, so let's let V be V1, V2. And then lambda is 2. And then if we multiply out the left-hand side, we get V1 plus V2, V1 plus V2 equals 2V1, 2V2. So this gives us two equations we can solve. The top row, that gives us V2 equals V1, and the bottom row gives us V1 equals V2. So we need V1 and V2 to be the same thing. But other than that, it doesn't matter what we take them to be. So we could choose V1, V2 to be 1, 1. So that's an eigenvector corresponding to the eigenvalue 2. And we can do the same thing for 0 as well. I think for 0, we'll find we need V1 to be minus V2. So an eigenvector corresponding to eigenvalue 0 is 1 minus 1. So eigenvalues and eigenvectors are very important they have a lot of different applications in all kinds of areas of maths. So one example is if you want to solve a vector differential equation, if you have something, so if x is a vector valued function, something like x equals x1 of t, x2 of t, x3 of t, and then you have some differential equation involving this vector valued function x, you can often use eigenvalues and eigenvectors to solve it. So one last example of eigenvalues and eigenvectors. Let's say find the eigenvalues of the matrix A, which is going to be 1, 0, 2, minus 1, 0, 1, 0, 1, 1. So let's solve this determinant of A minus lambda I. So here lambda I just has lambdas on the leading diagonal. So this is going to be 1 minus lambda 0, 2, minus 1, minus lambda 1, 0, 1, 1 minus lambda. And we need this to be equal to 0. And then we choose a row or column to expand along. So let's choose the top row. And then we get 1 minus lambda, lots of minus lambda 1, 1, 1 minus lambda. The 0 in the middle we can ignore, and then plus 2, lots of minus 1 minus lambda 0, 1 equals 0. And then we can expand, so this is minus lambda 1 minus lambda squared minus 1 minus lambda, and then minus 2 equals 0. So now let's multiply both sides by minus 1, and we've got lambda, we've got lambda 1 minus lambda squared plus 1 minus lambda plus 2 equals 0. And then let's see, so this is lambda 1 minus lambda squared minus lambda plus 3. So this is lambda, lots of lambda squared minus 2 lambda plus 1 minus 1 plus 3. So this is lambda cubed minus 2 lambda squared plus 3. And then, if we think a little bit, let's see, so if lambda is minus 1, I think that works, doesn't it? Because minus 1 cubed minus 2 times minus 1 squared plus 3 is minus 1 minus 2 plus 3, which is 0. So lambda plus 1 is a factor. And then the other factor is going to be lambda squared. We need a plus 3. But this gives us plus 3 lambda, so we need a minus 3 lambda here. And that also checks out to give us minus 2 lambda squared equals 0. Sorry, yeah, minus 2 lambda squared when we expand. So we get, therefore, lambda is minus 1, or this thing is 0, which gives us, let's just use the formula. Lambda is 3 plus minus root 3 squared, that's 9, minus 12 over 2. So we see we get complex eigenvalues here. We get 3 plus minus I root 3 over 2. So here are the 3 eigenvalues. And then, again, we can play the same game as before to find the corresponding eigenvectors. If we take a specific eigenvalue, like lambda equals minus 1, and consider, so A was the matrix 1, 0, 2, minus 1, 0, 1, 0, 1, 1. If we consider a vector v1, v2, v3 and set that equal to minus v1, v2, v3, and then we can solve this to find v1, v2, and v3. But there will be many solutions in general, so then you'll end up with, so, well, actually, let's just see how it works and then we'll stop. So we get from the top, from expanding this left-hand side, we get v1 plus 2v3 minus v1 plus v3, v2 plus v3 equals minus v1 minus v2 minus v3. So from the top row, we've got, we'll get v3 is minus v1. From the second row, we're going to get v1 is v2 plus v3. And v3 we already know is minus v1, so v2 is 2v1. And from the bottom row, we don't get anything new, we just get v2 plus 2v3 is 0. But we already knew that because v2 is 2v1 and v3 is minus v1. So that doesn't help us at all. So we can now choose. Let's let v1 be 1. We'll get then v1 is 1, v2 is 2v1, which is 2, v3 is minus v1, which is minus 1. So this is an eigenvector corresponding to the eigenvalue minus 1. So that's how to find eigenvalues and eigenvectors, which, so we'll stop there.